Good afternoon. I'm Brian Goldstein. I'm the Resource Conservation Manager of Jefferson County, and as such, energy is something that I'm keenly interested in and spend my days looking at. So it's good to see some familiar faces here as well as some new faces. Welcome to those first or second time visitors. If you have not been with us before, there's a local 2020 email listserv. It's basically a way we communicate about local energy issues, and I would urge you to sign up for that. Ellen, who greeted you, can actually get you signed up for that, and it's a couple, 2 or 3 emails a week, and it's a good way to learn about what's going on in our area around energy issues. Last month, we had 3 cell phones go off in the middle of the talk. And so I am actually going to I'm going to ask nicely for you, please turn your cell phones off so we don't have that happen again this month. The Energy Lunch now has a couple places where we have content about our program. The local 2020, l2020.org, is a wonderful site about all things sustainable energy, food choices, climate action, things like that. And so on the l2020.org site, there's actually a place for the Energy Lunch to announce our upcoming talks as well as summarize our talks in the past. And also the PT Journal, the PortTownsendJournal.com website is where we store our videos, which we'll be shooting today, as well as our past videos. So if there's a topic you'd like to go back and look at, it's been recorded over the last couple of years, and you'll see that on the PortTownsendJournal.com website as well. I'd like to thank our sponsors. Without our sponsors, we really couldn't do this program. So thank you, Alaska Power and Telephone, the Port of Port Townsend, Sunshine Propane, Power Trip Energy, Huber's Inn, who is now offering what Letitia's calling a living social voucher. So you or your guests can get 2 nights for the price of 1, and that includes a welcome basket with things like Fin River wine and elevated ice cream chocolates. So if you want to, Huber's Inn, talk to Letitia and tell her you heard about it here. And finally, we have a new sponsor this month, and that's Frederickson Electric. I don't know if Hans had a take off, but he was with us earlier. Frederickson Electric was founded by Eric Frederickson in 1974, and they've grown from a one-man operation to now become one of the largest electrical contractors in the Olympic Peninsula. They install everything from residential video and data networks to 480-volt equipment in commercial and light industrial settings, so they do the whole gamut. They've also been installing high-quality, high-performance solar PV systems in the local county areas here. So thank you to Frederickson Electric for being our newest sponsor. And I would like to announce that in June we have our upcoming talk there is something that might be a little controversial. Gary Peterson, who's the VP of the Tri-Cities Development Council, will be talking about the Hanford site, the Hanford nuclear site, and our nuclear energy future. Very interesting, with all that happened in Japan, and of course, that changed a lot of the climate in the world around nuclear energy. But nuclear energy is 14% of the world's energy, electrical energy today. So it's something that's a major player, and I'm sure a lot of us will like to hear about the future. You'll notice I'm using a microphone here. It's not only so you can hear me better on the PA, but it's also because we record these sessions. So therefore, to get the audio, we need the microphone. So a couple things. First of all, if you want to ask a question for our speaker today, I would ask that you wait till the end, and then we will pass the microphone around so that your question will be recorded and heard there. So thank you for that. So let's move on to this month's speaker. John Miedema is an internationally recognized leader and developer of biochar technology. In addition to doing long stints as an Alaskan fisherman and an electrical contractor, John spent the last 2 decades studying sustainable energy systems integrated with agricultural resource management. You'll hear a lot of that today. John was the founder of the Pacific Northwest Biochar Initiative, and he's taken a leadership role in biochar advocacy and research since 2008. And he's currently the CEO and Director of Research at Biological Carbon. So please join me in welcoming John today.
Thanks. Well, thanks a lot for inviting me here. My own personal background in this is I grew up around agricultural systems. My father and his family as a boy, they came over from the Netherlands, Dutch dairy farmers. My grandfather was indentured to my uncle. He moved out to Marysville, Washington, and became a dairy hand and a millwright at the Weyerhaeuser mill in Everett. So I was kind of around these systems. On the other side was commercial fishing. And so I was around agricultural systems growing up, and I was up in Alaska about 23 years ago in the Southeast. And I starkly remember the set that we had made, and in the set was 2 big sunfish and a school of mackerel. I had just read The Ends of the Earth by Isaac Asimov, and I quickly kind of accepted the fact that we were affecting the climate, right? So in The Ends of the Earth, Isaac Asimov talks about the polar regions, we're going to see those effects sooner, right? So I kind of sat down and started thinking about food systems primarily because I knew that for every molecule of anhydrous ammonia that we made that was our source of nitrogen for conventional agriculture, we made 1 molecule of CO2. I also knew that our tillage practices were fluxing CO2 out of the soils and into the atmosphere. I also watched agricultural systems change, right? The 50 head and 50 acre kind of model had now changed to 500 or 1,000 head on 50 acre. And the system was out of whack, right? So I started kind of delving into this. I started reading Buckminster Fuller, E.F. Schumacher, and the idea that really we had gained these knowledge that we have. I didn't want to regret the knowledge base that we had, but the knowledge base that we have is based on fossilized energy that we're harvesting from the ground, and shouldn't we maybe use that knowledge to maybe fix the system, right? So I started looking at, I think, being enamored with commercial fishing, the idea of integrated systems, because that's one of the most integrated systems there is a commercial fishing boat out on the water, right? We're surviving, we're harvesting. It's all kinds of systems in this tight little thing, little boat. And so kind of extrapolated out from there into a larger endeavor. And that it was necessarily going to be local, right? We had to get away from these huge power consumption systems, the food system that was based on massive transportation, that what we needed was design, right? We didn't need to really necessarily reinvent wheels, but what we needed was an integrated design, and to look not that these things weren't standalone systems any longer, and they shouldn't be. That maybe the cooling tower, that heat could be used for something else, right? So this was going to require innovation, but it wasn't necessarily going to require invention, but it was going to require high design was the thought, right? So the other thing is a new economic model, and I really very much enjoy E.F. Schumacher and the idea that the CEO needs to make 320 times what the janitor makes is a lot of the reason we're in the situation we're in, right? It can be driven by capitalism, but it doesn't need to be driven by laissez-faire capitalism, right? It doesn't need to be that type of a system. So looking back at agricultural systems, we have a finite amount of soil that's going to be tillable and available for arable food production. We have to make this a good nutrient-dense food, hopefully, right? I mean, the things that we're eating right now is food-like products. I mean, the nutrient quality of our foods is just diminishing, and it's because of the way we treat the soils, and we pump NPK in there, and we don't think about the whole entire system, right? We really should try to revive our rural economies by localizing, okay? What is biochar? Biochar is essentially, it's charcoal, but you've got kind of control over it. You're maybe manipulating the temperatures and kind of, for me, I try to have a lot of control because I'm trying to research the material, But essentially, it's charcoal. It's an open structure. It holds on to nutrients, and it holds on to water. And if we're looking at ag systems, if we look at cleaning up toxins, I have an ability to maybe grab onto heavy metals and grab onto hydrocarbons with it, okay, because of this open structure. I'll get into kind of what happens maybe in this one. So if you can imagine biomass going into this system, it's oxygen controlled, it's substoichiometric, there's not enough oxygen for complete combustion, okay? So what happens in the process of biomass combustion, it breaks down kind of in order of cellulose, hemicellulose, and then the lignin, okay? The cellulose and the hemicellulose tear out as gases out of the cell wall. The lignin and the inherent structure of the plant is left behind, and what you end up with is this beautiful matrix of internal galleries, right? That allows for nutrient exchange, allows for water holding capacity. There are certain chemistries that get developed depending upon temperature regime and feedstock, and that's manipulating, you know, as a scientist, I'm constantly manipulating things, but I can kind of manipulate that based on those things. I increase surface areas. I do things like bulk soil amelioration of the soil. So I can, on a clay soil, I can increase gas exchange, and I can decrease the amount of water that's in that. But on a sandy soil, increase the amount of water that's being held, and maybe increase some of the nutrient cycling. If that for a clay, so a clay, you know, you get the platelets laying up, the char gets in there, and those platelets lay around all of a sudden like this. They stack around it. So now those inherent, you know, the inherent nutrient value of a clay is quite high. The problem is it's not available because of the structure of the soil. This is actually, this kind of science comes from soil science. It started about in 1962. There was a soil scientist named William Sombrecht who came from the Netherlands. He heard about this very fertile soil in the Amazon. The name of the soil they were hearing about was called Terra Preta de Indio. It means the black earth of the Amazon. What we know about soils is that the jungle soils of the Amazon should be very infertile. These are oxalic clays, right? So Sombrecht went down there. And what he found was, in fact, this black soil. Around that black soil, and kind of the soil he found in this oval shape, around the outside of that was a terra mulata, which is a little more fertile than the parent soil. The parent soil is an iron-rich, acidic clay. It's very poor as far as what we're considering for growing agricultural purposes. The terra mulata is less acidic, more nutrients, and then you get to the terra preta. It's perhaps the most fertile soil in the world. As he dug down through and made his pits, what he found in there was that it was clearly anthropogenic. It had shards of clay in it. There was bones in there. There was refuse from human activity. And so as he looked out and started looking in the greater area, what he saw was causeways that linked these things together. This was a very large civilization, maybe in the order of millions of people living in the jungles, right? So whether by happenstance or by design, what the people found, this was Stone Age, this is 10, 12,000 years ago, right? What the people found is they cleared out their area where they could live. It wasn't a slash and burn agriculture, it was more of a slash and char type of agriculture. They'd go out into the surrounding jungle, bring the biomass into their villages, kind of burn their wastes in that, and what they found was a very fertile soil. Whether they did that on purpose or just found it later, it doesn't really matter. It's a fact, right? So this is a result. These pictures were taken by a friend of mine named Christoph Steiner, who had gone down there, and this was the same area right next to each other, the parent soil and the terra preta soil. Okay, they're still people go out there and harvest that and bring it into the local towns, for raised beds and that kind of stuff. So, what is this, and what's the potential? So, it actually has potential for all of these things: the food security, energy security. This is base load energy, right? It's biomass energy. I can use it when the sun's not shining, when the wind's not blowing. I can create jobs maybe through this process. I can certainly clean up water. I've been doing a lot of that. I can clean up toxic soils. I've been doing that. And I'll explain how this is actually a method for extracting carbon from the atmospheric cycle through photosynthesis. Now, there is a tendency around biochar, what I call drinking the Kool-Aid, right? There's people that see it and they think, oh my God, I'm going to save the world by this. It's part of a wedge, right? But it does have all these possibilities, so clearly we should investigate it. And that's why when I was studying methane gas production and I came across this because I thought it might be a way to make that more efficient, I locked in on it because if I understand that carbon and make that the central core of a design, all these other things can maybe play off of it. And it's part of an entire system, right? Major production techniques, you kind of have slow pyrolysis, which is maybe a more traditional method if you think about, kind of the old Missouri kiln, that type of thing. There's modern methods of doing it that are a lot cleaner than that. I personally use slow pyrolysis and gasification. Fast pyrolysis is a modern method where you use very fine material and you heat it really rapidly and you make quite a bit of bio oil and a little bit of char. And then gasification has been being done for a couple hundred years. And in that method, what you do is you take the biomass, you use some oxygen, and you can actually make a gas that you can burn into an internal combustion motor. I also do gasification. So how is it made? Kind of basically you have the biomass waste that comes in. It can go through sizing and screening, then drying, carbonization. The net kind of in the lab, there's some fugitive losses or whatever in the real world, but if you look at the mass balance, on a pyrolytic side, 3 tons going into the system, you end up with 1 megawatt of thermal drive extra, you end up with a ton of carbon, and you end up with the inherent energy that drives the system. It's an exothermic reaction. On the gasification side, if you have 8 tons going into the gasifier, you end up with 1 ton of char and 6.3 megawatts of thermal drive, okay? It's being made right now. It comes from gasifiers. We've been doing gasification. Like I said, it's happening right now on industrial scales in various areas. We can use all kinds of different scales of size. So you have the industrial size, you have more of a mobile unit, and then you have these T-Lud cook stoves that these are fantastic devices for the developing countries and the developing world. Right now in the developing world, I think, what was it, 2 million, 4 million people?
500 million 3-stone open fires every day, feeding 3 billion people every day.
Right, so those 3-stone fires, what you end up with is emphysema in women and children. Millions of women and children. The #1 killer in the developing country of women and children is emphysema from the 3-stone fire, okay? Also, the thing that happens with 3-stone fires is the fuel comes from primary forests generally, right? And the other thing that happens in the 3-stone fire is women and children have to go out and harvest that fuel, and terrible things happen to them in that process. Where does this feedstock come from? The feedstock is waste material, and it needs to be waste material. We can't harvest primary forests for this. It doesn't make any sense on many levels, economic or environmental, right? So we have to. It does have potential for being, kind of manipulated and destroyed by big money because you do have potential for biofuels. So me personally, we want this to be sustainable, right? So the first thing I started doing is putting together sustainability practices for the entire biochar world because we want to be self-policing and we do not want to do what the rest of the world is doing around biofuels. We want to be very cognizant of what we do. I come from the forestry sector. That's where I work. We have huge problems in the Oregon forests. I know we have the same problems around here, maybe a little bit less, but I don't think so. Our fuel load has gone through the roof. We've been putting out fires, and the reality is, when you look at it on a big picture, I'll get a little esoteric, but the Aristotelian idea of the 4 elements, right? Earth, water, air, and fire is imperative. I mean, that's a reality, and that exists all around us. And then we eliminated fire, and fire is the unifier of all 3 of those things. It affects all 3 of those things. We eliminated that from the environment by trying to put it out, and now we have these fires that are crown fires that burn the entire forest instead of these low, coal-burning fires that were traditionally the way the forest kind of, took care of its diseases and took care of these types of things, right? So what it can do for the forest is maybe we can do this in the woods, and as much as I enjoy a good bonfire, I see it as a tremendous waste, right? When I go out there and light them off in the forest, Yeah, it's cool and everything, but I'd much rather be able to turn this into something that's useful, right? So how is this a carbon reductive methodology? So we all know fossil fuels are going to put carbon in the atmosphere. These were taken off of the cycle millions of years ago. It's no longer on the kind of balance sheet of the Earth, and then we shove it up in there and it's throwing it off, right? The fuels, normal biomass, if we burn it all the way to ash, it's going to be a net zero sum game, right? Now biochar, when I put it into the system, if I'm harvesting my material properly, right, I'm getting it from a waste material, it's going to be fluxing back into the atmosphere. It has a life cycle of around a decade in the Northwest. I take and I put it through this process. I harvest this energy. I yield carbon, and that carbon has a half-life in the order of 500 to 1,000 years. And that carbon, then I use it for something, right? I find value in that for society. Either nutrient exchange or cleaning up toxins is what I've been doing. Water holding capacity. Now, if I take this material and I do it in an area, let's look at the developing world, right? These are generally very poor soils. Now, if I take this carbon in a very poor soil and I add it to it, I can show many, many papers that shows net primary productivity increasing 150, 200%. I'm not going to see that increase in a mollisol of the Midwest, but I'm certainly going to see it in a developing country that has very poor soils, Haiti, the Congo, right? And so now what I can do is maybe these folks can gather these little stoves, cook their fuel on grasses, right? Take that char and put it into their poor soil and increase that net primary productivity right around their village a little bit. Do that again, continue that cycle, and all of a sudden now they have a fertile soil. Now they don't have to do slash and burn agriculture anymore. Now they don't necessarily have to go out far distances and start to collect their fuels. Now for us, I can't stress enough how this is part of a whole system. This is integration. This is what we need to do, okay? This is what I'm driving towards, is trying to build these systems so that we integrate them together so that things like methane gas production from bio-waste, from food waste, and from dairy operations is linked together with composting operations, is linked together with biochar production, right? Because all these things can play off each other and the co-products can benefit one another. The co-product of the carbon that's produced, I take the nutrient-rich liquor that comes off the biogas plant, and I mix that carbon with it, I grab the nutrients out, I clean the water, I take the fiber-rich fraction that also comes off that plant, and I co-compost. Now I hold on to these organic acids that develop in there that has food value for microbes. Those impregnate that internal matrix of that carbon, and then the microbes start to go in there as food source, right? They find a food source and they can grow into it. The other thing that starts to show up is more and more hypha, mycorrhizal fungi. You start to build the food web of the soil again, and you start to get nutrient-dense food again. So as a researcher, I needed to be very specific, right? So this needs to be a commodity if we're going to do enough work. We need to take gigatons of this stuff out of the atmosphere, right? We're at 400 parts per million right now. We need to take it down to 350. So this has to be driven. Yes, we want the villagers to do it too, but us in the developed countries, we need to do this on a pretty massive scale, right? So it's got to be part of an economic model where this is co-product from energy production. We have to do a very high, rigorous design so that it's done and it removes CO2 in the process because of my location. Where I located at a timber yard because I knew all that biomass was coming in there. It's already there, I just move it over and I carbonize it, right? So now I make it in a stabilized form. And at the same time, it's a very dynamic material. The pHs can be adjusted, the chemistries within it can be adjusted. I want to do this in an artful manner that I can put it in its right place so that I can be, kind of get its best use, right? So I can make a very alkaline material for a very acid soil like you guys probably have around here because of all your rainfall. So it can be a liming agent. If I want to put it into a compost regime where I want the pH to maintain at about 6, I can do a lower temperature char. I can hold the pH at about 6, and I can hold on to the ammonia as ammonia, right? I don't lose it as NOx into the atmosphere. NOx is 320 times, I think, worse than CO2 on a life cycle analysis basis. And now I have a compost that I haven't lost the nitrogen out of, and it's still a plant available. So this is just this is just a description of how dynamic the material is. We made chars across temperature regimes of wood and grass, and yeah, I don't need to look at that. So anyways, this is a description. This was done by Johannes Lehmann from Cornell, and this is a description of what, so we're looking at across a temperature regime here, right? And we hit in this area, and all of a sudden a bunch of things start happening. So we do see the carbon recovery gets lost, but that carbon recovery is going to get lost anyways from rotting or whatever, right? However, we hold on to about 30 to 20% of it in a form that's stable. Let's see, what surface area goes up, right? Because of all that stuff. See, surface area goes up. Cation exchange goes up, not always, but it can. And the pH goes up. So what this model was done by Marco Kailuet down at Oregon State University. What this is describing is what portion of it becomes a stabilized form, okay? And it's this turbostratic crystalline carbon. And this is the potential that you can hold on to of the carbon. And basically it's a description that we can hold on to about 25 to 30% of it in this form that has long half-lives. Why is that? When you look at biomass, this is biomass that's gone through quite a bit of temperature. At the end of it, what you end up with is this carbon ring, right? Well, as that hydrogen finally gets driven off, you have 4 valence shells that the carbons need to fill. They just swing around and grab another carbon. So now what happens is you go to that temperature regime, you build a lattice work of double carbon. It's not quite a double carbon bond, but close enough. It builds in height and width, and now you end up with this very stable material that it doesn't, behoove the wee beasties to crack and try to get the energy out of because it costs them more, right? That's why we end up with these long-term ability of that to stay in the soil. So it doesn't decompose easily, but the edge structures do, right? The edge structures do break down, and we end up, and the other thing that if we have minerals involved in this, minerals get in the way and they become exchange sites, okay? So while it doesn't break down, it does slowly oxidize, right? After it's sitting in the soil, or if I manipulate it with steam, or if I use ozone or something like that when I'm screwing around with it, I can get these oxygen functional groups to show up. Now I can start to do things like grab up heavy metals, exchange nutrients and hold on to them so they're not lost in the getting washed out, right? And the plants can harvest them using the hyphae of the root. I hold on to all of these minerals. This is just a description that I'm also holding on to organic toxins and inorganic toxins in this process. So what this is, I was outperforming activated carbon sometimes for cleaning up toxins, and I couldn't quite figure out what was going on. So I had a professor buddy of mine do some XRD scans, and what we ended up seeing was carbonates and silicates and sulfur functional groups. And the reason I was outperforming activated carbon was because I had these minerals involved in there. And so now when I have these carbonates in there, a carbonate is a -3 ionic state, okay? Most of the metals in the environment are a +2 ionic state. I've got a -3 ionic state holding onto a +2. It's highly bound in there. And it doesn't get lost unless I use a high molar acid to extract it. So when I'm using it in stormwater situations, I can have it sitting in there. The zinc comes along. I bind it up with a carbonate or a silicate. It's a dynamic material. Some of those things are amphoteric, so they'll switch charges depending upon the pH of the solution. The silicate is always going to be a negative, however. So I can do both cation exchange and anion exchange on the same material. It's very, very unique in the environment. So this is just a description of some of the things we saw. So some of the acid groups that are left in there, these acid groups also bind up toxins, right? So these acid groups show up through the temperature. I don't know, I'm kind of going off a little bit. Let's see, so why would a timber company get interested, right? Well, so I worked for Thompson Timber and Starker Forest for about 4 years as their director of biomass energy. And basically what that allowed me to do was just do my research. I didn't have to go chase grants. And they're unique family forest company. Both of them, they've been down there 100 years one, 150 years one. They have concern about their rural environment, right? They have concern about, and which I imagine that exists in this community. We're concerned about what's going on in the forests. We're concerned about how we're affecting the waters. We wanted to reutilize old infrastructure. This is kind of a typical timber yard. You can just see how much biomass is laying around there rotting. So this is a chipper plant that we have down there. These chips that come off the top screen, that's what I use for my gasifier. I'll describe what my system is. That is my most refined fuel, right? It's just the overs off our chipper plant. That's kind of what they look like where my hand is. And then this is just more of that rotting material. This is what I use for gasification. This type of material here, it can have rocks, whatever, minerals, any size doesn't matter as far as density of it. That I can pyrolyze, which is a separate system, right? So now I can take kind of this more refined fuel and I can actually run an internal combustion motor with it. The pyrolytic side, I can take kind of the waste, like you imagine the chipper trucks that are coming around here and cleaning up around, that stuff can be pyrolyzed. And that stuff is very good for cleaning up toxins because the amount of minerals that are involved in that, right? There's not a lot of minerals here, but I can make good clean gas there. This is kind of a process flow. So I have this gasifier. I didn't want to use fossilized energy to be my thermal drive, so I chose gasification because I can run a gasifier basically as a throttle. So now I can make chars from anywhere from about 300 degrees centigrade to about 700 degrees centigrade. I have thermocouples all over it, so I can monitor it. So now I can make about 100 pounds an hour of this material. I can take that out and I can make enough of it so we can do research. That was the point. And I need to have provenance behind the material so that any results I saw, I could correlate back to something and I could make a statement of why this happened. So we went and sourced a Pacific class gasifier. This was built about 25 years ago. This technology has been around a long time. This happens to be one of the best designs that was ever built. So that's called Pacific class because it was built for the plateau of Papua New Guinea. 2 of those gasifiers ended up at a doomsday cult over in Montana. Y2K failed to go off quite right, so they all sued each other. This ended up getting bought and taken down to a nursery down in Northern California. And when I got involved in this process, I called up my buddy Tom Miles, who's an engineer over in Portland, Oregon. And I said, Tom, I want to run this retort, but I want to use a gasifier to do it. Where can I get a gasifier? And he helped me get this down in Northern California. The thermal drive from that is I consume 45 kilograms an hour, about 100 pounds an hour. The flame temperature fluctuates from about 1,000 degrees centigrade to about 1,200 degrees centigrade, or puts out about 500,000 BTU. Then I went about building a machine. We tried to source one, but I looked around the old paper mill, and I'm pretty good with the cutting torch, So it went into that pile and scratched my head for about a month, and found an old fuel tank, cut it in half. Found some refractory brick behind my buddy's ex-wife's house. And so the reason these candles are sticking out, because that flame comes in as a tangent, and then those candles that are sticking out cause that flame to tumble. And so now I end up with that heat. It helps the heat to get into the refractory, right? So then that kind of converts the temperature that's coming out of that, or the wave, from a kind of a high frequency wave to a long penetrating wave, right? So now the refractory heats up, and I have an interior tank that I built from an air tank, and then we made a cone on a press brake, and I ran an auger up through the middle of it that we drive with an old street sweeper motor. Put these things on the outside so the combusted gases have a tortuous path to get out. The furnace operates at it tries to go to about 1,200 degrees centigrade, but that's pretty torturous on my metal, so I try to keep it under 900, and then the exhaust gases come out of there. That's just the burner. You can't really kind of use a suction device to get those gases out, so I use pressurized air coming out in that burner, and that creates a low pressure area, and that sucks the gases then out and entrains the combustion air into the combustible gas. And then it gets up to temperature, right? And those gases come out from the top and back into the hearth and around the outside, and then it starts to drive itself. So I get it up with the gasifier. That's just more pictures. That's just, I mean, see, these things can be simple. Like this is an old extension off of a trailer that got bent. I cut it off, found some old C-clamps out in the shop, cut those off and put a plate on. I'm valving gases with this that are around 400 degrees centigrade, costing about $20 in material. It'd be $5,000 for a valve like that, stainless steel valve, easy, maybe $15,000. That's operated for about 4 or 5 years. The in-feed hopper on the top, I got an old knife valve. I load it in charges, right? It's kind of semi-continuous. I drop these charges in about every 15 minutes. The exhaust gases come up over top of that valve. The exhaust gases are anoxic. You know, they're rich in CO2. They're under pressure. That keeps the oxygen out, so I don't have any issues with explosions, right? So that opens up. Biomass drops in, and then I close it. And when I'm trying to make a low temperature char, I'll flare to the side. This flame here is about 6 feet long and probably about that high. It's just pouring out of the side. And that's when I'm trying to control the temperature for a lower temperature, right? So that's the machine. That's me flaring the gases to the side. It's about 14 feet tall on the retort side. So this is the gasifier here, and this is the retort, and they're just linked. I take the producer gas and valve it over here, so it dries my pyrolytic retort. This is just a description of like every run I make. I do temperature. I watch the temperatures so I can correlate back. What are the markets, right? So I came in this from nutrient cycling. The price points for a farmer is a little too high right now. You know, we need to get this up to industrial scale, so I started looking at remediation. That's where I've really been doing most of my work the last 2 years as far as in the field, is cleaning up toxins from stormwater, cleaning up polycyclic aromatic hydrocarbons, all kinds of hydrocarbons. You know, this stuff works really well. You know, like when that oil spill happened, I quickly got an aquarium and filled it up with oil, threw carbon in there, it sucked it up. Then I took that carbon and I burned it, right, and it made a great fuel. I sent the information to BP and they didn't really want to talk to me. But we've used it for cleaning up mine tailings. We can increase, you know, plant growth in very poor soils around mine tailings, that type of thing. So this was done by Professor Beasley, just so we can see a visual description. I don't know how well you can see that, but basically you have a soil that's got metal toxins in it, right, without char. Down here in a lower column was a soil that had char involved in it. You leach it out. Can you guys see that? I don't know if you can see it very well. Well, anyways, I can see it really good on my screen. What it shows is that the toxins get bound up. Okay. This one we did. So I made some chars out of manures for particular chemical reasons. I made them at 2 different temperature regimes, but I was comparing it to granulated activated carbon. This was from sediment from a Superfund site, okay? So what we saw, you guys can see this algae develop, and you can see how it's moved throughout the whole sediment layer. This was in a single layer like this is, right? Well, after a couple weeks, we saw this stuff move around, and what that indicates is a lot of chemical activity, and then we saw this algae bloom. And then we couldn't find the PAHs anymore. They had been consumed by the microbes. So what happened there is I put a lower temperature char in there because it has food value, so that increased the benthic community and gave them a place to base off of, right, and build up their numbers. And then they moved out and started consuming those PAHs and breaking them down into CO2 and water is what happens. So we've been doing some remediation work. I've been working with a company called Sunmark Environmental out of Portland. This was going into an old metal mill, and they were really getting nailed by DEQ for their discharge. So we went in there and we put hydroseeder mixed with 10% char And in here, this got excavated, and there's char down in here. And the upshot is these guys are making benchmark now. We increased their growth of their plants around there, and it was, it's quite successful. Now we just went out and in North Dakota, where they're doing all the drilling or whatever, 2 or 3 times a day, about 5 acres of the North Dakota prairie gets covered in a blowback that includes salt, water, and hydrocarbons, right? Well, we went out there and sprayed this thing, and they couldn't get anything to grow, and we sprayed this out there, and right at the beginning of winter, we're actually able to get the prairie covered back in prairie grass. So now in the stormwater, zinc in urban environments generally comes off of the metal roofs and off of 3-tab roofs because we don't like moss, right? So we put zinc up there, it sits out there in the sun, zinc oxides develop. DEQ discharge rates are about 86 micrograms per liter. When we were going out and testing this, we were seeing 3,700 micrograms per liter, 4,200 micrograms per liter. So zinc is very destructive to fish, right? Copper levels are really through the roof. So we just put a tote underneath there of biochar mixed with some shale, and we're able to get these guys down to benchmark. So now we're looking at trying to include this in just the soils that are going into what they call green streets, right? So on the front end, we could go back to the composting facility. We mix the char into there. We get these organic acids show up in the char. It benefits the compost regime. It benefits the char. We get activation sites in there. And then we put it into this environment and we bind up the toxins, right? Just integration, design. Can you guys see? I don't know if you can see these numbers, but so this was 730 micrograms per liter, and we took it down to 40. These are different chars that we were just analyzing. 2,700 micrograms per liter down to 193. And in this case, all we would do then is add another tote, and then we could get it down to benchmark, right? This was a cut slope out by my house. It was like this for 10 years. We came in with that 10% char mix, sprayed this on there, and this was about 4 months later after that. All right, so I'm done. So I'm happy to take questions, yeah.
How about inoculation?
I don't know if it's on. Okay. Inoculation?
Yeah. I've drunk the Kool-Aid and fooled around with it at home, and I wonder, is there a lag time when you add it to soil? And if you're putting it in really poor soil, does it have to be inoculated with the good stuff before you do that?
Really poor soil, you're going to see benefits right away, right? I would always suggest, if you're using it for agricultural purposes, to impregnate it with nutrients prior. And a real simple way is compost, or soaking it in a fish emulsion, or putting it in a bucket and peeing in it, whatever you want to do. So, you gotta wait for that.
What's your sense of performance for the common Jolly Roger tea luds you see on the internet? Mm-hmm. Are they really producing a good quality biochar?
Well, when you look at good quality, it's kind of, it depends what for. For agriculture, certainly. Yeah, I mean, it's high temperature. It's got, in the biochar, like kind of the scientists, they'll say, oh, but it's got ash content. Ash isn't a problem. Ash is beneficial for ag, right? As scientists, we want to narrow it and control it, and they don't like ash. Well, ash is fine. I mean, if you start to get too high of an ash, you might have an alkaline issue that you have to be aware of. But really, if you just take that material and you put it into a compost, then it's going to kind of balance things out, right? If it's super alkaline and you put it into the compost, you might want to monitor your pH, because, like I was saying, if our alkalinity of our compost goes too high, we are going to lose the nitrogen. So if you monitor your pH and you maintain it under 7, try for 6 or a little over, and you can affect your you can acidify your compost through different means. But you're probably not going, you put it in your compost at about 10 to 15%, and you're probably not going to affect the pH anyways, but you are going to hold on to the gases and not lose them. Yeah.
Have you made any attempts to use the heat that you're producing?
On my machine, I use it for drying down material, so I dry down the feedstock with it. I'm building one right now for smaller holders, a design where it's got a coil that I can capture water heat, so I can use that for heating greenhouses, that type of a thing. So kind of, yeah.
I'd like to suggest one easy way, excuse me, one easy way to capture heat. I built a T-Lud wood stove for my workshop. Works like a charm.
Yep.
I create biochar, and I'm heating my shop. It holds about twice as much wood as a typical wood stove. The problem is my insurance man said it will invalidate your insurance if there's ever a problem. So I ran it to the junkyard.
Right. Well, another way to capture heat simply is you can make char in a cone-shaped device, right? Or a pyramidal-shaped device that's shaped like this so that when the heat comes out, it curls back on itself. And so then you get a good clean burn because you want to burn all those gases, right? So when those gases come up along the edge and they curl back and they burn, and as it consumes, you can cook on it. You can put a grill on it and cook on it and kind of capture heat that way kind of easily, right? So that's a method. And then if you go online, there's these T-Luds designs that you can cook on, and that's a way. Industrially, you have to find a heat user, but I can make so much heat. I mean,
What about particulates produced in the burning?
So when you think about particulates, generally the particulates that are going up into the atmosphere is that lignin. It's this very structurally sound material, right? So the lignin is held in this carbon, so you don't have the particulates as much.
So does that mean you've actually analyzed particle size and particle mass?
It has been done, yeah. I personally haven't on my machine. We have done it on some gasifiers and certainly seen particulate matter hard to find. Yeah. I can find that data for you and get it to you. Sure. You still, EPA is still going to require, on an industrial scale, EPA is still going to require the same kind of scrubbers and that kind of stuff because that's based on megawatts out, right? So that would still be necessary for the process if you were going to go to an industrial scale. However, it probably isn't going to be cleaning much.
With some of your designs that you've been using, do you see any of them as being viable for just waste management streams in towns like Port Townsend, where we have trimming companies and a lot of debris being created? Have you seen any of those sprung up anywhere, or any ideas on that?
Well, I've got all kinds of ideas. Yeah. That's not a problem. The design, they exist. The problem is, I think, it's the cost, right? So I think people are trying to maybe make this a traditional economic model, and we need to work together to do this somehow, right? And we need to co-locate and find value in all these streams that come off of it, and then the economics can start to work. We've done economic models where we're looking at the 3 tons in an hour, and if we find value in the heat at what the value of, at the time I think it was $5 per million BTU we were using. We had payback 2.5 years if we were seeing the char move out at $300 a ton, right? The bulk density is somewhere around 7 yards to the ton, so about $72 a yard cost or something like that. I don't know if I have that right, but somewhere around $100 per yard. Then the economics can start to work out. And then if there's any tipping fees involved, because on those numbers, I was using $30 per bone dry ton, which is what my cost would be for clean chips. But if there's tipping fees or zero cost, then the payback becomes sooner.
That is really a very quick payback.
Yeah, absolutely. Yeah, but it's the market build, right? That's why I stopped. Once I got to the machine where I could make enough, then I had to get the horse back in front of the cart and create a market. Because it's great if I can make all this black stuff, but if I don't have a market for it, it's not going to go anywhere. So that's why I started looking at what are the markets where it can go.
And I would like to invite anyone that's here. There's a workshop this weekend at 4 of us that are presenting the workshop on Saturday at the Grange from 9 o'clock to 4 o'clock. At Quimper Grange. We're going to be making 5 55-gallon T-Luds, the top-load updraft stoves. And in addition to that, we will have examples of the small gasifier from C-Char. We will have that C-Char 5-gallon stove. We're going to be, and other smaller gasifiers where we'll be doing a potluck lunch on the gasifiers. And it'll be a great example. Even if you don't have the time to come, just stop by and see what we're doing. And it is an excellent example of these in action. And I know on another note, I know specifically of a mushroom farmer in Squim that's using a T-Lud completely in his cultivation of mushrooms and the pasteurization of his straw. He's using one of these T-Luds to heat his water to pasteurize his straw. And it's finding the use for the heat, and it's instead of just burning it off. And that's what Lowell Dietz at Dietz Farm did. So come on by on Saturday at Quimper Grange.
So if I can touch on one more thing, which is the liquid aspect of this. So this process, when you carbonize, you're doing what's called basically destructive distillation of the wood. You tear it apart into component parts. So you have an exothermic non-condensable gases that you burn separately, but then you can drop out organic acids and you can drop out oils, right? Those oils can be a form of densified fuel that you can burn. The infrastructure for making those into a liquid fuel right now is a little bit, it's still in the research end, and we are doing work about some upgrading using some, what we call microreactors. I don't need to go into it, but it might be a way to get to a liquid fuel train. Right now, the reality of that for me, personally, I haven't been convinced that there's a way to take that oil and economically put it into an internal combustion motor, but we can certainly make heat with it and store it for heat. And we will be able to get to upgrade chemical building blocks type of things. I mean, there's phenols and aldehys and ketones and this type of stuff in there that are building blocks, but that stuff is still in the research field as far as I'm concerned.
Regarding the new economics side of this, to what degree do you see folks in the biochar sphere looking at making this kind of research and the innovation that's necessary available in the public domain and outside the patent system? Is that even a possible venue for implementing
you saw
this
my
on the scale
machine.
we want?
You saw the guts of that thing. I mean, I'm certainly giving it away. Not most people aren't necessarily, but I kind of always kick those guys in the ass whenever I get a chance, because we need something new, And so it's not rocket science. I mean, carbonization is, it's this second livelihood to man, right? So,
If you were primarily interested in producing heat, and the biochar was a byproduct, what fraction of the heat would you get compared to complete combustion?
Let's see. So you would end up with about 70% conversion to heat in a 70 to 80. Depends on the process. It depends. So that the caloric value of the carbon that's left behind is going to be what is lost, right? So if I hold on to 20% of it in that carbon form, that's 20% of my energy value. That's not harvested. So my whole point, what I'm trying to do is, we're going to take biomass and we're going to turn it into energy, right? We're going to do it. We're in the process of doing it. What I'm trying to do is prove that there's more value to society in that carbon than the caloric content, right? So right now, the caloric value of that carbon, depending upon what we're paying, is somewhere around 4 to 10 cents a pound. If I can, as a biochar trader, if that's what I decide to go into, and I can purchase it from the producer at 25 cents a pound, all of a sudden, every time they build a new plant, they're not going to make it a combustion plant. They're going to make it a staged combustion or gasification or pyrolytic plant, because they know they've got a commodity there that's worth a lot more than the caloric content, right? So that's what I'm trying to do by trying to ascertain what these markets are. So when I show that there's a market, and by the time I get done doing that, finally the big boys building those plants are going to have a better methodology because of the economic driver.
Do you believe the research that's...
Do you have any examples of small-scale agriculture that has really dove into using biochar in this bioregion in the Pacific Northwest?
Yeah, I mean, like in the urban infrastructure of Portland, there's a lot going on. I mean, the smallholders, people growing food, they're including char in their compost. I'm constantly dropping off bags of char down there to try to keep it going and get people's interest. I know animal farmers that are using it in their bedding to mitigate the toxic smells, right? You can use it at 1 or 2% in the bedding, and it stops the sulfur and the nitrogen, that toxic kind of smell that you gets knocked down from it. So just in the bedding operations, there's a lot of studies coming out of both Germany and Korea and Taiwan and Vietnam using it in animal husbandry, and you see decreased mortality, you see increased milk production, you see, and if you think about it, it makes all the sense in the world. The bovine gut developed on either the mollisol, if you're looking at our buffalo, or it developed in the charanzome of the steppes of Asia. These are fire-derived soils. And then we put these poor bastards onto cement, and of course they're going to be, their stomachs are going to be messed up. They produce way less methane when you include it in their food at about 1%. It's part of nature.
I believe the state of Washington is supporting an effort somewhere in the state to produce fuels in commercial quantities from biomass. How does that process differ from yours? Or is it,
are you talking about the torrefaction type of material when they're taking it for a coal plant?
No, for biomass. Biomass. Originally, the idea was biomass to aviation fuel.
Oh, right. Yeah, I know Washington State University is working on that with Boeing, and they're spending a bunch of money. I know that.
Have they flown anything yet?
No. I mean, but maybe there's a pathway, and we're working with these microreactors, and that might be a pathway. Basically what happened, we were doing this kind of work the turn of the last century with methanol production, right? And then we discovered oil in quantity, and it was a lot simpler and a lot cheaper, so that organic chemistry literally changed at that point. We started looking at these other ways, and they built the infrastructure in the cracking tower based on low oxygen and low acid material. Well, now we don't have the infrastructure, and who's going to build it, and you kind of run into those problems. So hopefully there's a way, and we're looking at these microreactors that we're using nano-etched kind of plates to extract those chemicals out, and that might be a pathway because you need to stack these things up. But the infrastructure just doesn't exist for liquid fuels right now out of it.
If a local farmer wanted to get a commercial amount of it for inclusion in their composting where they're using fish and chicken waste, where would they go? Where would they find commercial quantities around here?
Well, that's been difficult. We're starting to get more and more carbon available. You could get a hold of me. I think I can probably source it for you. So I mean, I've got my machine that I built, and There's other ways that it's being harvested from commercial boilers and that type of stuff, you know. And then we want to have a high degree of understanding where the feedstock's coming from. We don't want painted material going into it and blah, 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 blah. But they're starting to get enough interest and the ball's rolling enough that there is starting to get to be maybe commercial quantities available, like starting right now. It's just starting to happen. And so you're probably looking at price points of around $140 a yard or something like that. You know, maybe we can get it a little bit less depending on the volume. And if I can find any sourced locally or something like that. But coming from my area down in Oregon up to here, it would probably be somewhere around there. Anyways. So it's getting to be available.
I would just like to say, I don't believe that it's a question of either or in regards to fuels, liquid fuels, or this process. It's a question of and.
Yeah.
That there's need for both, and that can be supportive of each other. There are some major investors working in liquid fuels, but they are the type of investors that hold it close to the vest and not open source. Mm-hmm. We really don't know what they're doing.
And there's other pathways. Like right now, I'm working on a project where we're taking the char and on the back end of a methane gas plant, right, down in Junction City, Oregon. And right now we're just bringing the carbons there to see what kind of value I can get and how well I can take the nutrients out of there. You know, I've done it great on a bench, but I want to see how it works in the real world, right? Well, if I can prove that there's a market there and it makes sense, then what I can do is co-locate a pyrolytic retort, and I can take those organic acids and put them into the methane gas plant and their food value for the microbes, and we can let the microbes do the conversion to methane and then take the methane and condense it to a liquid fuel. That might make sense.
Okay, one last question.
You may have covered it. I was in here late, but what kind of toxicological screening is being done? This is a very new industry, both for animal feed and human feed and exposure.
Sure. Well, there's a couple of labs that we send the material out to, so that we do, if we change our feedstock, right? If the feedstock changes, we'll do an assay at Oregon State University. We do one, and then there's a lab down in California that I use also. So I have a readout sheet that tells me what was in it. Yeah.
Are other people doing that as well?
Quite a few are, yep. There's a soil control lab down in California set up a specific protocol for doing this testing, and it was based on a bunch of us getting together through a group that's called the International Biochar Initiative to set up what those testing protocols should be. And so it's all very open source and available on the International Biochar Initiative website.
All right, no, we're out of time here. I wanted to let everybody get a chance to leave. And if you have any other questions, John, I'm sure you'll stick around for a few more minutes afterwards. Yep. So please join me in thanking John again.